Okay, all right. First and foremost here, let's walk through our graphs. I handed everyone a piece of graph paper. Don't throw this away. This is your notes for the next couple days. I don't want to find them on the floor when you guys walk out of here. We're going to use these for notes. Just because what we're doing in the next couple days in here is transformations, looking at even and odd functions, looking at inverses, and it's nice if we have a graph to go with it. We're just going to do a couple things by hand every now and then, just because it kind of refreshes our memory what we're doing here. The goal today is just a quick introduction into the different steps for transformations. So, I'm going to put the little order up on the board here, just so you have it. So, the order that we have that I'd like you to write down. This is kind of like an order of operations for graphing. So, order of operations for graphs.
Just write this stuff down?
Yeah, this is something that you just need this checklist that I want in your notes somewhere. Okay? So, number one. Okay? Number one is a horizontal shift. Now the book, your textbook does not talk about this list. This is something that we're going to go through today. It's kind of our outline today. Number two, the second rule, is you're going to do some type of stretch or shrink. Now that works vertically and horizontally. So we're going to look at, how those apply. Three, we're going to look at some type of reflection. And the last one, number four, vertical shift. This order, for some reason, is not in your textbooks. It's something that you just need to know. Like, this is a generic order that I follow every single time when I'm graphing. When I look at a function and I see what they've done to it, I'm following this pattern to make sure that I sketch it in the right locations every single time. Question?
You should make an acronym and slap a patent on it.
I should. That would actually be really smart.
And you're so smart.
Okay. Anyway, let's talk about the idea here. So I'm going to give you a generic picture here. So
But you
let's
can't
say,
make money off it because you're a teacher.
Yeah, you can't double that.
That's double.
You just
No.
double dip.
if I make a textbook or come up with something, publish it.
Oh.
So,
Sure.
all right. So, f of x. Let's just give it a graph here. So let's say f of x looks something like this. We'll just kind of do like the parabola looking shape. Let's say that's my function. Okay. And what we're going to do is we're going to do a couple different things to it, just to give a sense for how this works. The first thing is how they horizontally shift something. So what they're going to do is they're going to take your function. They can either call it something like this. And I don't care what the function is, but if they want to horizontally shift it, right or left, up or down, here's what it looks like. If they want to go to the right, they want to shift this to the right. No matter how many numbers you want to go. What you do is you take your function and you're going to subtract a number off of it. And that will shift your graph to the right, however many spots you want by whatever your number is. So like for instance, if I want to shift it to the right 3 spots, this is what it would look like in your function. It's kind of like a composite function. We're going to talk about that a little bit too. So it's x minus 3. That's going to take this graph, and at every spot you see, it's going to go to the right 3 spots, and it will, so every spot that I have here is going to move to the right 3 spots from where it's at. And it'll just look like the same drawing, it's just been drugged to the right. Does that make sense, like what they're doing there?
Yeah.
Now, if they want to move to the left, you probably get the idea. So if they want to go to the left, you take your function and you add a number to the inside. So it's going to be some positive number. So if I want to go to the left 7 spots, you just add a 7. Okay. Make sense? Kind of recap of what we did in pre-calc quite a bit. This was, in pre-calc, this was like the 3rd section of the 1st chapter. Algebra 2 they covered a little bit, not in depth. Algebra 1 for sure they covered it. But this has been a long time ago. This is for you guys. We did this in pre-calc. It was like mid-September when you guys did this.
About a year ago.
About a year ago. Yeah, almost a year ago, but it was mid-September.
Good
Not quite.
So, now, the thing is, what we need to be able to do now is do this on the fly if they do multiple items to it. Not just shift it right left, but shift it right left, maybe reflect it, and go vertical a couple. So like we have to know the order we have to go in. So you have to follow these kind of basic steps. Okay? Does everyone understand the right and left thing? Okay, let's go to the next one. To stretch. All right, so if I want to, let's go vertical stretch. A vertical stretch, like tall-wise. What they're going to do is they're going to take a number and they're going to multiply it outside of your function. But all you have to make sure of is that the number you're multiplying by, the number has to be greater than 1. Whatever number you're going to multiply by. That will stretch it vertically. So if I want to be, 3 times taller at each spot, you multiply by a 3 out front. 3 times half of x. Something like that. That will stretch it vertical. So each dot here will go up 3 from where they're at. Questions with the vertical stretch. The idea, like each dot. Now the one at 0, 0 would stay where it's at, but everything that's off the x-axis would actually move. So the weird thing is, vertical stretching doesn't affect x-intercepts, where it hits the x-axis. It only affects everything off the x-axis. That's the weird part. Next thing, if I want to shrink, so I want to shrink this. It's the number you're going to multiply out front just has to be less than 1, but greater than 0. So it's got to be some fraction that will compress it down. It'll look like it's getting wider, but it's actually just compressing lower. So everything towards the x-axis. X-axis numbers, x-intercepts will not move. Everything else will get, that distance closer. So if I put, like let's say I did a half out front. Now it's literally half as tall in every single spot. So on the original graph here, this spot was 1 and this spot was 1. Now they're at half at those locations. So it looks like it's getting wider even though it's not. It's just shrinking and compressing. The things that, like, how do you know if that's true or not? I look at where the x-axis number is. Did the x-axis move at all? If the x-intercept didn't move, then it's compressing vertically. That's something I look for. Questions?
Nope.
Okay. Next one. Let's do the horizontal stretch and shrink. These two we're going to really focus on tomorrow. Today's goal is to really get to these 3. Like, can we do these all in one problem? Then we'll get to composite functions and we'll get even them out. Okay, let's do the horizontal shrink and stretch. This is the part that's really goofy. Horizontal is always backwards than what you think it is. So, when I threw negative numbers, I moved it to the right. When I threw positive numbers on the inside, I moved it to the left. On horizontal stretch, to stretch it horizontally, the number on the inside with the x that you're going to multiply by. Because that's how you affect stretch or shrink, you multiply. The number on the inside has to be less than 1, greater than 0. That will stretch it horizontally. You saw it earlier. It looks like it's compressing when it could be stretching. Twice as long. You'd actually put a half in there. Half x. That would be twice as long horizontally. We're going to look at how to do that tomorrow. We're going to look at looking at like Desmos and throwing in a bunch of different things to see how it just instantly changes that graph. But if you want to shrink something, like compact it, now you put whole numbers on the inside. With the f of x, this number would be greater than 1. That will compact it. Because what it's going to look like, what it's going to appear to be, if you threw like a 3 in here, it'll look like it's getting taller. It's actually compressing it horizontally, inwards. Questions on the horizontal. It's always backwards than what you think it is. That to me seems backwards than what I would expect. because the whole half and whole number idea. Shrink versus stretch. All right, reflections. There's only two types of reflections. Okay, so the x-axis reflection. If you want to reflect across the x-axis, here's all you do. You throw a negative sign out front of the f of x. That will throw it across the across the x-axis. So if I threw a negative sign out front, here's what your graph would look like. It'll dump it over. If you want to throw it across the y-axis, now we won't be able to see this one because the graph I picked is kind of symmetrical. But if you want to go across the y-axis, you throw the negative sign on the inside. That'll throw it across the y-axis. Now I drew something that's kind of symmetrical, but if it wasn't, you'd be able to see that they would flip sides. Questions? And then the last one is a vertical shift. Vertical shift is literally just taking your graph and dragging it up and down. The graph will stay the same, it just physically shifted from where it was, where the origin was. So to do a vertical shift, let's say I want to shift it up. All you do is out behind your function, just add a number. That will shift it up. Notice it's outside the parenthesis. So if you add like a 4 back there, it'll shift the graph up 4 spots. I do f of x plus 4, whatever that function is, that will drag it up 4 spots. Do the same looking graph. But again, you do these things last. So if you're going in order, and I'm doing multiple things to this thing, you have to see kind of order that you have to go in. Okay, questions with that? Okay, I'm gonna throw 3 things together. We're gonna draw this on the next graph, and we're gonna see how we do. So here's what we're gonna do. So this graph over here, let's call this g of x. So go to your second graph. If you haven't drawn anything up to this point, go to your first graph. I don't really care. Whatever your graph is, here's how I want you to put. On one side, I want you to go diagonally up to -2, 3, and then draw a line that goes over, like horizontal from there. So go from the origin, go to -2, -2, 3, and then go a line straight across. On the other side, just draw a squiggly line kind of going up diagonally. That way you get a sense for how I'm going to move stuff around. Now, sorry. I was expecting a call today.
Oh no, now I have to stop the camera.
I believe that they're gonna get counted now.
I should. That's actually something I would think about. Terrible. Ah, I'll cut it off. All right. Okay. All right. So we got a graph, right? Well, let's do like multiple things to it. So on this one, instead of like, I don't want to do any like stretching. That we'll save that for tomorrow. Let's move this thing to the right 2. So I'm gonna go. So how do I move this thing to the right 2? What do I need to do?
-2.
Okay. On the inside, right? That'll move it to the right 2. Okay. Let's do a reflection across. Let's go a reflection across the x-axis. So I put a negative sign out front, and let's move it up 3. Up 3. So now, let's go to your next graph, and we're gonna. So you should be on your second or third graph. I don't know what graph you're in right now.
3.
Okay, 3 for if you've been drawing every picture up to this point. We're going to take this thing and we're going to manipulate it with all these different ways. So we're going to the right 2. We're going to reflect it across the x-axis, and then we're going to move it up 3 spots. So just kind of giving you a sense. This thing is moving to the right. So I'm following my order. So horizontal shift first. Right 3, this thing's going like this. It's going up, 2, 3, it's kind of going over. So this is what it looks like when I first horizontally shift it. But now I gotta reflect it. So it's going down like this. So far, here's where I'm at. So this is to the right, reflected. And now, the last thing is to move it vertical up 3 spots. So up 3 will be here, and here's what I have. This is the final drawing. You see like the process that I go through. Question?
Doesn't it go right 2, not 3?
Oh, 2, right. 2, sorry, 2. Yeah, 2, thank you. Didn't touch that. Easy fix there. Let's see. Yeah. There. Right, 2, thank you. Okay, makes sense? Right 2. Reflected it, and then went up 3 spots. And there's your spots. If you follow this order, this is exactly what the graph should look like. So you can kind of manipulate and kind of move things wherever you need to. You just have to follow the pattern. Now, obviously, the thing we're going to look at tomorrow, how do we stretch and shrink at the same time? What happens if you start throwing negative signs on the inside? How does that look? We're going to look at all this stuff. Tomorrow is a good day to bring the Chromebook for sure, because we're going to do instant fixes. So we can see kind of what it looks like on Desmos, so we don't have to draw these by hand. We can just instantly see what happens when you start mixing all this stuff together. Make sense? Okay. Let's stay with this. Let's go to our next topic. I want to talk about 2 things here. I want to talk about even and odds functions, and then I want to talk about composite functions, because that's the stuff we go into after this time. So, but these are our main checklists. Okay, evens and odds, let's start there. Okay, this is symmetry of a function. Symmetry is how you can look at a picture and see if it's perfectly balanced from the right to the left side. Now, obviously the drawing I just did a little bit ago was not symmetric, right? Because you can tell, like, the left side was doing one thing, the right side was doing another. They are not balanced right and left across the y-axis, right, or across the origin, okay? So there's 3 types of symmetry. There's even, odd, and neither. Or neither, however you want to say it. Those are your 3 options you have for symmetry. It's either even, odd, symmetric, or it's not symmetric at all. This graph I have right here is not symmetric. It's not balanced. Let me give you an example of an even symmetric. Yeah, so this example I'm showing you here is an even symmetric function. The right and left side are perfectly the same picture they're supposed to be. Sorry, my art is really bad, but you get the idea, right? The right and left side look balanced. No matter what the picture is. So let me give you another option here. Maybe it was doing something like this. Okay, it's the right and left side do the same thing. Okay, across the y-axis. So even symmetric is across the y-axis. How you actually check whether your function is symmetric. Number 1, you can look at it visually. Like, to me, that does look like it's balanced, right? Other than my terrible art. The other thing you can do is if you take your function, whatever the formula is, because you'll get to see your formulas, right? Whatever your formula is, and if you plug a negative x into it, like where all the x's are, you plug a negative x in, and you simplify the problem, and it turns out to be the original thing you started with. That's an even symmetric function. To give you an example, like how that would work. If I gave you a function like this, f of x, let's say the formula is x to the 4th plus x squared plus 1. Right? Took my function, and I plugged in negative x's everywhere. What happens to the negative signs when I put it to the power of 4? It goes away. They go away. When I square it, the negative sign goes away. And then the 1 just stays where it's at. Do you agree that this is the same thing that I started with? Yeah. That's an even function. If you were to graph it, it would look symmetrical right and left side. The shortcut for me are all the powers, even powers on all the variables. That's why they call it literally an even symmetric. All the powers are evens. Even the number 1 has an even power in theory, right? Because this is x to the 0, which is still an even power. Okay. Questions at all about that even? Okay, odd symmetry. Odd symmetry. It's when it's across the origin, not the y-axis. So if I was doing something over here, and I go the other direction, and it goes the opposite way completely, diagonally, not straight across the y-axis, but diagonally, that's an odd symmetric type of function, right? That's the concept. Or maybe a good way to show it is if I did something like this, and then the other side I did the opposite. That's an odd type of symmetry. It's diagonally from each other. It's across the origin. So everything this side is perfectly balanced this side. Diagonal. So it's across the origin. Now, how you can tell, obviously with your function, if you plugged in a bunch of negative x's, it would turn out to be the original function, but just negatives on the outside. Everything would be opposite. So that's if you were to look at your problem, and it was doing something like this. You were to plug in negative x's, everything would be negative in the long run. So what kind of powers do I have here? Odd powers. So it's an odd symmetry. No constants. Everything is an odd power. Questions with odd symmetry? So I wake up Brown before I draw on his face.
Luke.
Brown, I'm gonna draw on your face.
Do it.
Brown. Oh, Brown is so happy. Wake up.
You got
All right.
Morgan Freeman spots.
Okay. All right. Next. The next thing we're going to talk about, other than odd and even symmetry, now what we're going to talk about is composite functions. This is the last thing today, last bit of notes. Probably will be done in 4 minutes. Okay, so composite functions. If you take a function, let's say your function is 2x plus 5, right? And you have another composite function, or another function which is x squared minus 1. I can do a composite thing where I do something like this, where I want f of g of negative 1. That's a composite function. I want you to go inside out. I want you to solve what is g of negative 1 first. Once you have that number, that's a digit, then you're going to do f of whatever that digit was. Does that make sense? So you're doing like one inside of another. Now what it looks like, if you were to mix these together, it would look something like this. Right? You're taking the g function, plugging it in f, taking this thing, plugging in f where there's x's. This is what it actually looks like what you're doing. Most people just do them one at a time. That would save people a lot of effort. So if I did negative 1 and plug it into g, negative 1 squared, 1, subtract 1, 0. Then you just take 0 and plug it into the other one. That's like the easiest way to do it. 0 times 2?
0.
Plus 5?
5.
So your answer is 5. Like your overall answer is 5. Or you can just do the negative 1 here and go from there. It would be the same answer in the long run. It's just however you want to look at it. Questions what we're going to do with composite tomorrow. Now why I'm bringing this up, because obviously when we start doing this type of stuff, it's composite. We're mixing items on items on items. So we have to know how to handle it one at a time. Questions?
Nope.
Okay, we're done with that.
Can you go over something?
That was it?
No.
Do you have questions? Yeah. We'll go over questions, so bring it up. We'll talk through it. I'm going to turn off the camera.